Welcome to satellite communication course. So today we see few numericals on a satellite link and we'll conclude the model 2 on the satellite communication. Now you write down the statement here. An isotropic radiator located on the equator transmits 200 watt power full stop. What is the flux density? What is the flux density at an altitude of 1000 kilometer? What would be the flux density received at received at the geostationary orbit? Received at the geostationary orbit. Next, what is the difference in flux density in dB? So in this altitude for the geostationary satellite is given for a geo is 35768 kilometer. It is given now in the statement. Now our aim is about to find out the power flux density here. Our aim is about to find out the power flux density at an altitude of 1000 kilometer. Means we have the R is about 1000 kilometer and a power transmit power we have that will be of a 200 watt. Okay, transmitted power that will be of a 200 watt. So if you consider that a flux density at a altitude, in that case F becomes what will be the transmitted power by 4 pi R square. So PT, that is nothing but a transmitted power here, that is about 200 watt is the transmitted power and the altitude of 100 kilometer here. So power flux density, that is F is equal to what? A 200 divided by 4 pi into we have a 1000 square. So if you saw all that, you'll get that power flux density, that is F is equal to 15.9 into 10 to the power minus 12. Next, we can find out that F, it is in a dB also. So if you see that power flux density in a dB, so that will be of a 10 log of this one value, 10 log of 15.9 into 10 to the power minus 12 is equal to minus 108 dB. That is about a power flux. And this one is about what? Watt per meter square. So that's about a dB watt we have. That is about the output. It is in the dB watt here. You can see. So now that is about a first statement. Next is about the statement. What will be the flux density received at the geostationary orbit? So means we have that a power is same. Okay, transmitted power is same. Only that altitude instead of altitude 100,000 kilometer, we consider that altitude of a 35768 kilometer. Okay, so you can see that F is equal to what? Another value. We can say F2 here. That will be of a 200. Then the transmitted power is same 4 pi, and that R is nothing but what? A 35768 kilometer. That will be the square. So that is about the flux density received at the geostationary orbit. Okay. So now in that case, we have the Earth here, and that orbit will be nothing but a geostationary orbit. Okay. So in that particular case, that orbit, what will be the flux density received at the geostationary orbit, at this particular orbit? What will be the here at a geostation? So transmitted power, that will be on the equator. We say it transmit, in earlier case it transmit the power at an altitude of 1000 kilometer, and here it will transmit to the georbit. So we consider that instead of that, this is about your R, that will be of 1000 kilometer. Now here we have the transmitted power. Okay, likewise. So now you can solve it using this. You will get that if that output is about a 1.224 into 10 to the power minus 14. Then difference between that, what is the difference in the flux density in dB? So you can find out that F2 in dB also. F2 in dB, that will be of a minus 139.1 dB. Then difference, that is about another statement, that will be the difference uh, is equal to F1 minus F2 is equal to minus 108 minus minus 139.1 dB, and that difference will be a 31.1 dB. That is about the difference. So this one is about the statement here to obtain the difference for the your particular link. Next question: a satellite receiving receiving station has a dish antenna, has a dish antenna with an aperture area of 7.5 meter square. To stop, it received a signal at 4.2 gigahertz. If the aperture efficiency if the aperture efficiency is assumed to be 70%, comma, find the gain find the gain of the antenna. Find the gain of the antenna. Now here our aim is about to find the gain of the antenna. So the gain of that antenna is equal to what will be the antenna aperture efficiency into 4 pi a by lambda square. That will be the gain of an antenna. Now that aperture area is given, that is A is given, received frequency signal, that is F is given, and aperture efficiency that A is given. Now then from the frequency you can calculate that what will be the lambda. So lambda is equal to what? That is C by F. F is a 4.2 gigahertz. If you could put that 10 to the power 8 and F is equal to 4.2 into 10 to the power 9. So you will get that lambda becomes a 0.0713 meter. That will be the lambda. Now you can put that all the values here, that is for the aperture efficiency and all. Aperture efficiency is a zero point 0.7 into we have a 4 pi, that is about A is about a 7.5 divided by lambda, that will be of a 0.0713 meter square. So if you solve it, you'll get that gain is equal to 12977.5. That will be the value of a gain. And if you want a gain in dB, then 10 log of 12977.5 with respect to 10 here. So after that, solving that gain, you'll get that gain will be 41.13 dB here. Okay, 41.13 dB. That is about the gain in a dB. Here the gain directly we calculate with respect to aperture efficiency and everything. And here that gain is in a dB that we can calculate here. Next one, a satellite transmits, a satellite transmits 1 watt of power at 4 gigahertz. Sorry, a satellite transmits a 1 watt of power at 4 gigahertz with an antenna with an antenna having a diameter having a diameter of 1.4 meter. Find the EIRP of the satellite. EIRP means what? That will be the effective isotropic radiated power. That is nothing but what? It is nothing but a PT into a GT. Or we can write the AIRP in terms of a dB also. So PT in dB plus GT in dB. Now if you see that here, that given term, we have the diameter of an antenna, that's D here. Then we have the frequency, that is about a F with about a 4 gigahertz given. And then from that you can calculate that what will be the lambda here. And a power transmit, that will be a PT, it is given. Transmitted power, that is about a PT is given. Now our aim is about to find out only the GT here. What will be the gain of a transmitting antenna? So gain of a transmitting antenna, okay, so that gain is nothing but what? A pi, because the antenna diameter is given, so that's why it is about dish antenna. So for a dish antenna diameter is d, so that's why the gain of the dish antenna is what? Pi into d bracket square. That is about a gain. So now we can calculate that pi, where is the diameter, and for the lambda that will be a c by f. So c is equal to what? 3 into 10 to the power 8, and f is equal to 4 into 10 to the power 9. Okay, this one is about a c and this one is f. So lambda is equal to what? A c by f. Just we have written here 3 here and F here above. Okay, otherwise 3 by 8 here and divide by 4 into 10 power 9. So from that you will get the gain. Gain value is about what? 58.64 bracket square. That will be what? A 3439. That will be the gain. Generally, EIRP we can write in terms of a dB here. So gain in a dB for this is nothing but a 10 log to the base 10 3439 is equal to, that will be of a 35.36 dB. That will be the gain of an antenna. Similarly, we can calculate that PT into dB. So that will be what? 10 log of 10, and that PT is given, it is 1. So after solving that, you will get that 0 dB back. That will be the transmitted power. So EIRP is equal to, that will be a 0 dB that we have, plus we have that 35.36, that will be the dB value. Okay, no need to write the unit here. So, so EIRP is nothing but what? A 35.36 dB here. Okay, that will be the effective isotropic radiated power. Next, an earth station, an earth station transmits 10 watt of power at 2 gigahertz with an antenna with 30 dB gain, 30 dBi gain. Find find the flux density, find the flux density at a satellite receiver in 400 kilometer orbit, in 400 kilometer orbit here. So that's why from that, if you see that a earth station, that is about a transmit side, so we have the power transmitted, that will be nothing but a PT here, that is the transmitting power at 2 gigahertz. The frequency is about 2 gigahertz. We can calculate the lambda with an antenna with a 10 dBi gain. Okay, that is about a gain of a transmitting antenna is given. Okay, so gain of a transmitting antenna is given. So now we need to calculate here what will be the flux density at a satellite receiver in a 400-kilometer orbit. You can say that a earth station transmits this, and we have the satellite, it is present there, and the distance r is about a 400 kilometer. Now we consider here EIRP is equal to a PT into GT, and a flux density F is equal to what? EIRP divided by 4 pi r square. That will be nothing but a PT GT by 4 pi r square. Put the values here for the gain, that is about a 30 dB it is given. Now you convert that gain because it is in a dB. So gain in a dB is equal to what? 10 log of 10 raised to the power whatever the gain value we have. Gain in a number. So now it is in a dB it is given, that is about a 30 dB it is given. That's why we have a 10 log of whatever the gain term for the transmitting antenna. This 0 0 get cancelled, then antilog of it 10 to the power 3, that will be nothing but the gain here. So a gain will be a 1000 now. Okay, now the gain value will be 1000. So power flux density, we can find out that PT is about a 10 watt. Here we have the 10 watt of a power here. Okay, that is about 10. And GT that we have calculated, that is about 1000 here. And then we have the distance of the orbit is about a 400 kilometer. Okay, you write down a kilometer, okay, because we need to consider it is in every time it is in a kilometer, because I sometimes I have even I forgot to write that it is in a kilometer here. Okay, so there 1000 kilometer, and here again kilometer that I have written. I forgot to written that is in a kilometer. So kilometer means 10 to the power 3 again here. Okay, and then you solve it. Okay, so now we have the F is equal to, that will be 10 into 1000 divided by 4 by 400 kilometer here. So that will be a 4.97. Okay, 4.97 nanowatt per meter. That is about a flux power density. Then we can consider that another example here. A geostationary satellite, has a downlink, has a downlink frequency, has a downlink frequency of 4 gigahertz. Full stop. Find find the free space path loss. Find the free space path loss encountered encountered by the signal encountered by the signal when when it arrives at a ground station. When it arrives at a ground station. Now our aim is about to find the free space path loss. That is about a LP here. LP is a free space path loss. The frequency is given. Okay, we have value of a frequency is given, that is about a 4 gigahertz now. And the satellite orbit, that is about a geostationary one. So that R is nothing but what? A 35768 a kilometer. Okay, that is about a R, because R is not given anywhere. So that's why we can use that R value directly and you can put here. But before that, you should know that what will be the path loss. Path loss, that will be LP is equal to what? A 4 pi R by lambda bracket square. That will be the a path loss. So now I can put that R value and lambda value, you'll get the path loss directly. Because for a geostationary satellite, that R is equal to what? 35768 a kilometer, that we have considered now. Okay, assume that R is equal to 35768 kilometer for what? For a geo orbit. But this LP, we are getting the value in terms of some number. So we need to get that value of a path loss in terms of a dB. So that's why we have a factor of what? A 20 log of R, that is for R, plus 20 log of, we have the frequency here. It is in terms of a gigahertz now. Okay, plus that factor for C, Lambda is equal to what? C by F. 4 pi by C. And that factor is nothing but what? A 92.44. That will be the getting a answer is about a 92 dB. So path loss in a dB, that will be what? 195.55 dB. That will be the answer. So R, you put that this one value. F in a gigahertz, that is about a 4 gigahertz is given, and you can put that, so you'll get that path loss, that is about a 195.55 dB here. That will be the answer for this. Next, a geostationary satellite transmits a geostationary satellite transmits 5 watt of power, 5 watt of power with an 5 watt of power with an antenna having a having gain of 28 dB. The downlink is operated at the downlink is operated at 4 gigahertz, and and the receiver antenna the receiver antenna is a dish with diameter dish with a diameter of 3.6 meter. Compute the EIRP. Compute the EIRP transmitted and the power received by the receiving station. Power received by the receiving station. Assume the receiver antenna. Assume the efficiency. Receiver antenna efficiency to be zero point 0.7, and all the other losses losses to be 2 dB. All the other losses to be 2 dB. Now, if you see that statement, transmit power, that will be 5 watt, that will be a PT here, and the gain is about 28 dB. That will be the gain given. That will be the 28 dB, and it is operated at a frequency of 4 gigahertz. And dish diameter, that will be 3.6 meter is the diameter here transmitted, and the power received by the receiving station. Assume the receiver antenna efficiency, that is about eta A is given, and other losses, that is nothing but a system loss, or you can say that system loss margin. Okay, so that is given, that is of a 2 dB. Now here our aim is about to find ERP transmitted and the power received by the receiving station. So we will calculate first what will be the EIRP, complete the EIRP. So EIRP is equal to what? PT EIRP in dB, that is nothing but PT in a dB plus GT in a dB here. So the gain of the transmitting antenna is 28 dB. Gain of the transmitting antenna, having the gain of transmitting antenna, that is 28 dB. But the satellite transmit the power is about 5 watt. So gain is in dB right now. We have value gain in dB, but we doesn't have the value of transmitting power in a dB right now. So PT dB is equal to what? 10 log of transmitting power watt is 5 dB. So you'll get the answer that will be of a 7 dB watt. So put that 7 plus, this one is the answer. You put here 7 plus gain is about a 28 dB. So you'll get that 28 plus 7, that is about a 35 dB watt. That is about the answer. That is about the EIR. Now next we need to find out the power received by the receiving station. So power received by the receiving station, that will be the PR is the power received, is equal to what? What will be the EIRP plus what will be the gain of a receiving antenna or in dB. Okay, that is power received in a dB now. Okay, EIRP, the gain of a receiving antenna, that is again in a dB, minus what will be the path loss in the dB, minus what will be the system margin, that is in both. All the terms are in a dB now. Now EIRP, we got the term, that is about the EIRP, that will be a 35 watt. Okay, 35 dB watt here. But what will be the gain of a receiving antenna? Now the receive antenna here, it is about a dish antenna is used, so we can calculate that gain of a receiving antenna. So to calculate the gain of a receiving antenna, so GR is equal to what? A 4 pi epsilon E divided by lambda square. That is about a gain of a receiving antenna. So AE is what? A effective area, effective aperture area, but it is given here, that is the diameter of an antenna, that is about 3.6 meter. So our aim is about to calculate that effective aperture area, that is about AE, and then a path loss, and that will be nothing but what? A 20 log of 4 pi r by lambda, that is bracket. Or if you separate out the term each and every that we have seen earlier, that is LP is nothing but what? 20 log of r plus 20 log of f plus 92.440. You can use this one, or you can use directly, that will be of a 20 log of 4 pi r by lambda bracket raised to 2 here. Okay, we can write that way also. Now first we need to find out what will be the gain of a receiving antenna. Now the gain of a receiving antenna, that is GR is equal to 4 pi epsilon E by lambda square. Sorry, gain is equal to 4 pi epsilon E by lambda square. Now then, effective aperture area, that is AE, is equal to antenna efficiency into physical aperture area, that is about a AR. Okay, that is about a physical aperture area. So physical aperture area, that is AR, is equal to what? Since the diameter of an antenna is given, and that antenna is about a dish, so that's why that equation for the physical aperture area, that is AR. Okay, we can write here physical aperture area, and this one is what? Effective effective aperture area. Okay, this one is about the effective aperture area. So that is about a pi d. That is about, we can say that we have the uh, physical aperture area, that is about a pi d square by 4 here. Because we have the antenna is given, and in that case, that the values for this gain of an that effective aperture area is nothing but what, a pi d by, what you can say, pi square here. So now we can calculate that from that d diameter that is given. Diameter is given, that is about a 3.6 meter. Diameter is about a 3.6 meter. So it is equal to what, pi to 3.6 bracket square by 4. Then we'll get that 10.18 meter square. That is about the aperture area. Then effective aperture area is equal to eta into AR. Now the efficiency is a zero point 0.7 given. Efficiency is a zero point 0.7 given. So that is about a zero point 0.7 into 10.18 is equal to 7.125 meter square. Then put that all the values, you will get the gain. So before that we shall calculate that what will be the lambda here. Lambda is equal to what? Is C by F, that is 3 into 10 to the power 8 divided by a frequency that is about a 4 gigahertz is given. 4 into 10 to the power 9. So then you will get that is lambda is equal to 0.075 meter now. Put the values in the equation of a gain here of a receiving antenna. That will be what? A 4 pi into, that is about 7.125 divided by lambda square, that is about 0.075 bracket square, is equal to 15917.4. Then gain in a dB, that is 10 log of this particular term, you will get that gain in a dB. So that gain in a dB is equal to what? A 42 dB. That is about a gain here. Next, about calculate that a path loss. Path loss is equal to what? LP is equal to what? 20 log of 4 pi r by lambda. So then is equal to 20 log of 4 pi into r. R is equal to what? 35768 kilometer. Okay, that is about a kilometer square, not square, 768 kilometer. Okay, mix 30 here. Divided by lambda, that is about 0.075. Okay, it is about a 0.075. After solving that, you'll get that LP in a dB, that will be 195.6 dB. Okay, path loss in dB. So power received power, that will be PR, that will be in a dB now, is equal to what? The EIRP plus GR minus LP minus LM. So it is equal to what? EIRP is equal to 35 plus GR, that will be 42 here, minus 195.6 minus 2, that is about a system margin loss. So that will be equal to what? Power received in terms of a dB, that will be minus 121.6 dB watt. Okay, if you calculate that in terms of watt here, so that will be a zero point 0.7. Okay, 0.7 watt, 0.71 watt. Okay, that is about your answer. Now that this one is about the equation. If you see that here we have geostationary satellite transmitted power of this one is given now, and the transmit frequency is about 4. Here the downlink is of a at 4 gigahertz given. Okay. Now if you consider that uplink, then it will be different. Okay. So then uplink frequency will be different, and then we need to calculate that power for this, all the antennas, and then similarly you can calculate that gain of an antenna. Now, so you can calculate that if it is the for the different antenna for the different frequency, so then your answer will be different here. Next, we can calculate that the noise temperature. The noise temperature, the noise temperature at the input of at the input of a satellite receiver is 350K full stop. Input to the receiver, input to the receiver is an FM modulated, FM modulated video signal occupying a bandwidth of occupying a bandwidth of 18 megahertz. Stop. Calculate the noise power. Calculate the noise power at the receiver input in dB. Now the noise power is given as is equal, or we can say that noise power is equal to K dB. K is a Boltzmann constant and is equal to what? 1.38 to 10 to the power minus 23, and the temperature, that is T, is equal to 350 given. Okay, input noise temperature at 350 K, that is about a T. This one is nothing but a T term. And then we have the bandwidth of 18 megahertz, it is given. So that's why we can write here T is what? 350K here, Kelvin. Okay, 350 degree Kelvin. uh, the answer we have, then we have the bandwidth of 18 megahertz. Then you'll get that n is equal to 869.4 into 10 to the power minus 16 watt. Then we can write it in a dB also. So you can write n in a dB is equal to 10 log of 869.4 into 10 to the power minus 16. That will be n in a dB is equal to what? Minus 130.61 dB watt. Okay, that is about the noise in a dB watt here. So another example can solve it regarding that temperatures and all. For that, we need to consider that a diagram for the noise powers and all.